Hi everyone, in this video I'll walk you through the UFO demo built using SecureMR on the Pico headset. In this demo we'll use headset's video see-through cameras and small face detection model to track the user's eye. So let me just show you the project. So this is a UFO project which basically follows your movement in real time. So whenever the model detects your left eye, a tiny UFO appears in front of it and it tracks you. So the goal of this tutorial would be to help you understand how Secure MR connects machine learning, camera data, and 3D rendering step by step. Don't worry, you will find everything under this documentation in the Secure MR section. So let's start by adding the using statements at top of our script. We bring in system text and threading for general C# features and background threads. We also import the Unity XR, PXR, and SecureMR framework. The Unity engine is used for basic Unity functions like game objects and scenes. So now we'll set up some variables that define what the app will use. We'll do that in the demo class. So the first one is a face model. This will hold the machine learning model that detects faces. Again, it's a text asset, so you need to convert the model into that. And next is UFO GLTF asset, which is a 3D model of a UFO. Then the anchor matrix asset, a smaller helper file that feeds the model's outputs aligned with the camera image. And after that, we have some variables, num frames to run, which controls how long the demo runs. It's set to -1, which means it'll run continuously. And after that, we have interval between pipelines, which is 0.033 seconds, which means we'll update roughly 30 times per second. And finally, we have the width and height of the camera frames we'll capture. Now we are creating a few private variables that will handle the main logic of our UFO demo. So the first 5 lines are provider and pipeline. Think of the provider as the main manager that connects secure MR to the headset. It gives us access to cameras, sensors, and all the processing tools. Then we have 4 pipelines. Each one handles a specific task. So let's say we have the VSG pipeline. It captures video see-through frames from the headset cameras. So we have provider here. Think of provider as the main manager that connects secure MR to the headset. It gives us access to the cameras, sensors, and all the processing tools. Then we have 4 pipeline here. So the main reason of pipeline is like each one handles a specific task. Let's say we talk about VSG pipeline. It captures video see-through frames from the headset cameras. The model inference pipeline, it will run the face detection model to find where the eyes are. And the map 2D to 3D pipeline, it takes 2D eye positions from the camera image and converts it into a 3D point in the space. And finally, the render pipeline will take a 3D point and draw the UFO at that location in the real world. Below that, we are defining some global tensors. So it's basically a container for data, kind of like a flexible box that can hold images, numbers, or matrices. We're using these global tensors to share data between these 4 pipelines. And we are, for example, the VSG output left unit 8 global and the right unit 8 global will store camera images. This will, the timestamp will keep track of when each frame was captured. And the camera matrix global, it stores the camera's calibration info. Then we have the current position and previous position, which helps us track the UFO's position smoothly between the frames. And finally, we have left eye UV global. This will store the 2D position of the left eye detected by the model. That is the key data we'll use to position our UFO. Next, we're creating a few more variables. So these are mostly placeholders that will be used inside each pipeline. If you remember, the global tensors we created earlier are like shared storage. They keep the data that all pipelines can access. But these placeholders are like temporary input boxes inside each pipeline. When a pipeline runs, we'll tell it, hey, take the data from this global tensor and plug it into this placeholder. It's a clean way to connect everything without having to rebuild the pipeline every frame. So first we have these placeholders, which we will be using for the VST pipeline. So these represent the left and right camera images, timestamps, and the video see-through pipeline. This is going to be used by video see-through pipeline. Then we have a few model inference placeholders here. So the model config sets up the face model run, how the face model runs, and anchor bytes. It's the reference table for the model, and the left eye UV placeholder will show the 2D eye position that comes out of the model. Next are for the 2D and 3D mapping. These are for the difference between current and previous position to track and like to make the UFO move smoothly between the frames. Finally, we have a placeholder for the GLTF, which is the 3D object of the UFO. And at the bottom, we have a few variables for setting timing. Now in the awake function, we are turning on the video see-through, which lets us see the real world through the headset. We also set the app's frame rate to 30 FPS, which is a good balance. Next, we have some flags for the pipelines. Then these are just switches that tells us when each pipeline, like the camera model render pipeline, has finished setting up and is ready to run. We also use a concurrent queue called main thread actions to safely send small tasks back to the main thread. You can find all of this in the documentation too. Finally, the pipeline lock is like a safety lock to make sure only one thread edits the pipeline at a time, so nothing breaks while things are loading in the background. Next, we'll just write start and update function. So in the start function, we begin setting up everything our app needs to run. First, we create a provider which connects SecureMR to the headset and manages all the pipelines. Then we create 4 pipelines, one for video see-through, one for the face model, and one for mapping 2D to 3D, and one for rendering the UFO. After that, we create global tensors to prepare all shared data containers. Now, each pipeline is then created on a separate background thread so the app doesn't freeze while loading. Once a pipeline is ready, we mark it as ready to use. And if something goes wrong during the setup, we just print the error in the console. Now, similarly, in the update code, we run the pipelines in order, but only after all of them are ready. We also space them out in time. The camera runs 0.33 seconds, the model and mapping runs every 0.5 seconds, and rendering happens every frame. This keeps the app smooth and efficient while updating all the parts of the UFO demo continuously. Now let's look at how we connect SecureMR to the headset and prepare the camera data. So in create provider, we are basically giving it the height and width of the window. In the create global tensors function, we are going to define the tensors which we had taken as variables earlier. So in create global tensors, we are going to define the tensors which we had written earlier here. So it's done using .create tensor. Again, you can find all of this information in the documentation. So we are basically giving that image its attributes, like what height it would be, what width it would be. And along with that, we are also defining the global tensors. So for the UFO detection. So, so this is our first pipeline, the VST pipeline. So here we are taking the placeholders for all the tensors which we created earlier, because in a pipeline you cannot have global tensors. You need to have a placeholder here. And now here we are creating an operator. So this is the rectified VST access operator, which actually grabs the left and right images, the timestamps and the camera info from the headset. And we use set result to tell the operator where to put each of those outputs. Then we use assignment operator, which copies the image data and changes it from bytes to floating point numbers, so it's ready for processing. And finally, we have an arithmetic operator, which divides the pixel value by 255. This step normalizes the image so the model can understand it better. So overall, this section sets up our data flow. It connects the camera feed, it cleans it up, and gets it ready for the AI model to use it in the next stage. Now we'll build the model pipeline that finds the eye in the camera image using SecureMR. So this is the code for it. It's a bit long. So first, we make two placeholders inside this pipeline, one for input image and one for left eye UV output. UV is the point. Placeholders are empty slots here. Um, the next, we create two tensors to hold the model's raw results. UFO anchor for the detect box coordinates and UFO scores for the confidence scores. So we basically tell SecureMR how to run the model by adding input and output mappings to model config. Then we create a run model inference operator. We feed an image with set operand and tell it where to write the results. The model's boxes are relative, so we apply the anchor table. We convert the anchor bytes into floats, make a tensor for the anchor matrix, and prepare UFO landmarks. It's a tensor to hold pixel aligned boxes. Then, using the assignment operator and small slice tensors, we just copy the parts that are needed and then run one arithmetic compose operator that transforms the relative boxes into pixel coordinates using the anchor data. Then we pick the argmax. So we pick the best decision using the argmax operator on the score to get the top index. Then we reshape it to a tiny matrix and one where needed for slicing. And we also use a couple of assignment operators to copy the best box out of the big list into a single best face landmark. And then finally, we just extract left eye XY points from that best box. And we define a small slice for the first two values and then copy them with assignment operator. All of these assignment operator, argmax operator, assignment arithmetic composer operator, all these are found in the documentation. So this means when this pipeline executes, we'll end up with the left eye position, return into a placeholder, and ready for the next step to turn it into a 3D spot in the world. Now we'll define another pipeline. We'll turn the eye point from the image to a 3D position in the real world using the SecureMR. So the first step should be to create a placeholders for all the tensors which we created and whatever we are going to need. Then along with that, if we want, we can also create some local tensors, which would be just for this pipeline. So we start by making placeholders for this step. The eye UV point, the frame timestamp, the camera matrix, left, right VST images, and final placeholder where we'll write the final 4x4 pose. The first operator I would like to talk about is UV to 3D in camera space operator. So we are feeding it the UV point, timestamps, and all the data. It returns a point XYZ in the camera's 3D space. Then we copy that point into a tiny 3x1 matrix. Then we do two small tweaks. First is the element-wise multiply operator to flip the Y, so it matches our world conversion. Uh, then we do arithmetic compose operator to add a small offset, so the UFO isn't exactly on the eye. Next, we have get transform matrix operator. We provide rotation, translation, and small scale. That gives us a 4x4 transform in the camera space. Then we convert from camera space to headset world space using this operator. This is the same timestamp to give the left eye world transform. Finally, we combine it with arithmetic compose operator that multiplies the left eye transform into the pose at point. Then we write that result to our output placeholder. Now it's time to draw the UFO. So, so in create render pipeline, we have two placeholders, current position read and previous position read. We also make a interpolated position tensor. This is a local tensor here. And we have two operators. So to keep motion smooth, we use the arithmetic compose operator with a formula, which is like you can see it here. This blends most of the old pose with a little of the new pose, so the UFO doesn't jitter. Then an arithmetic operator copies the interpolated pose back into the previous position read. So next frame continues smoothly. Next, we have a GLTF placeholder for the model bytes. Finally, the switch render status operator. Um we feed the GLTF placeholder and the interpolated position as the world pose. So now we are running each pipeline one by one. In run VHG pipeline, I create something called a tensor mapping. It's basically a list that connects placeholders inside the pipeline to a global tensor. So here I'm saying use these camera images from the global data, and then I run the pipeline with execute command. This grabs the latest camera frames from the headset and prepares them for processing. Next, in run model inference pipeline, I connect the processed image from VST to the model input placeholder, and I connect the model's output, which is the IUV data, to our global tensor. And when I execute this pipeline, SecureMR runs the face detection model and fills in the eye position. Then in run 2D to 3D pipeline, I map the 2D eye positions into 3D space. Here again, I connect all the needed tensors, and the result is written to current position global. This gives us a full 3D position in the real world where we'll place the UFO. And finally, in run render pipeline, I link the current and previous positions along with the UFO model itself. When this pipeline executes, SecureMR renders the UFO model smoothly at the latest 3D position, completing the full pipeline flow from the camera to detection, then mapping, and then finally rendering.